Hey there, Isaac here. Well, this is a first video I've made in about 3 weeks, and I do plan to be more consistent with my uploads of at least once a week. I do know that some time ago I did say that I'd make at least 3 in a week, but I don't know, nothing really got in the way exactly. I didn't even, it's not really that I forgot about the channel. I don't really know what it was, but anyway, I just plan to make more videos in the future. So, this video today will be about radiation and nuclear decay, which are one of my favourite topics in all of physics. Now, radiation is everywhere. It comes from the sun, from us, from your morning coffee. It comes from everything. And it's not anything really to be scared of. Though there are radiation that is dangerous, but you'll most likely never encounter in your lifetime. Anyway, radiation is just a form of energy, and it comes in 2 categories. So there is ionizing, there's ionizing, and non-ionizing, or for short, I and Ni. Ionizing radiation is the type of radiation such as gamma and UV radiation that we get from the sun. And I'll explain in a little bit what that is. But those types of radiation can be harmful, and because they have so much energy, they can damage the DNA in our cells, which can cause mutations and cancers, which is not fun. Well, non-ionizing on the other hand is such as radio waves and visible light. Yes, light that we receive in our eyes, colour, is because of radiation, but non-ionizing radiation, which is safe. Though technically non-ionizing radiation can still be harmful, just in different ways, such as infrared, which is heat. Heat is infrared, so technically they can be dangerous, just in a kind of a different way. So, and radiation is another 2 kind of categories, not necessarily just ionizing and non-ionizing. There's also radiation such as decay, so particles, and radiation that's on the electromagnetic spectrum. So we have the electromagnetic spectrum, and then we have particles. So the electromagnetic spectrum is to do with electromagnetic so basically photons. It's to do with photons. Every type of electromagnetic radiation is actually just a different energy, a photon with different wavelength and just more energetic photon. That's why if you've ever heard that light, which is visible light, which is in kind of the middle, is photons because it is. So in the middle here, you would have visible light. And outside of it, you go to UV. For it, you go to infrared. That's infra. Infrared, as I said, is heat, and UV is a type of radiation. Ultraviolet is what we get from the sun. And it's a range wavelength from 10 to 3 of the size of the waves. Radio waves are 10 to the 3rd power meters size, and gamma at the very other end is 10 to the negative 12 meters in size. So gamma is very small and interacts with atoms in the nucleus of atoms. Radio waves very, very large and don't really interact with the nucleus of atoms, but do interact with structures. But this isn't, as I said, the only form of radiation. Well, I will make a video about electromagnetism because it's very interesting. It's not just about that, but that is one of the parts of it. Now, when these are the 6 forms of radiation. So there's alpha, beta, gamma, delta, epsilon, and zeta. Now you may be wondering, wait, I've only ever heard of alpha, beta, and gamma. What's delta, epsilon, and zeta? Well, these three are a lot more rarer forms of radiation. That's forms of radioactive decay that still form, they're just rarer, but they still definitely should be talked about. They're not actually called these, but I think why not keep the Greek alphabet going. So, put my pen in my hand. Alpha is represented as a kind of like, I still can't draw it very well. It's kind of like that. It's like a weird fish / A thing, because it's the Greek letter for A. And this is beta, which is kind of like a B, but kind of the stick kind of goes down. Gamma, if you want to just do it simply, is kind of just a capital Y. Delta, you could do it like this, is probably not the best way to do it, but it's like a Z, like a weird Z to 6. Epsilon is, wait, hold up, let me just double check. I have it here. Epsilon. Where's epsilon? Hold up, just give me a second. Epsilon. I'm pretty sure epsilon is that. It might be the way around, but that's what I remember. Now we have zeta. That's probably the best I'm going to do. That's basically zeta. So it's again like a Z, but instead of going to a 6, it kind of curves, making this like weird mouth, and then going at the bottom like a squiggly line. As you keep going down the alphabet, alpha, beta, gamma, and so on down to zeta, each one was discovered a little bit later and later. I think it was either alpha. I think alpha radiation was discovered first, then beta, because actually, yeah, we'll get to our point. So alpha radiation is a nucleus of helium. So helium is 2 protons, 2 neutrons, and 2 electrons. But this is just 2 neutrons and 2 protons, making it positive by 2. It can penetrate. It can just be stopped by paper, but it can kind of just penetrate. But it's a very weak form of ionizing radiation. Beta radiation is a little bit complicated, because we get introduced to a particle that I haven't really mentioned yet, which is a neutrino. So beta radiation is an electron, and it's also an anti-electron neutrino. I'll explain kind of why that is in a sec. Gamma is just, you kind of write it like that. That's another way you could write it. This was a small form anyway. It's really just a very, very excited photon. And alpha, beta, gamma. Delta is, wait, hold on, give me a second. I forgot what I did. Give me a sec. What did I do? I must forget. The neutron. Neutron radiation. When an atom decays a neutron. Epsilon, which is a neutrino, it's anti-neutrino or neutrino, and I might just be able to fit it out, just put it here. Zeta is a proton. decay, when an atom undergoes decay, it is because it's in an unstable state and wants to get to its most stablest form, which it does by ejecting some form of radioactive decay. For example, we have an element which is the isotope of uranium 238. It decays via alpha 2 positive, and that radiation, well, it ejects it, becoming a different element and a different isotope. So to work back to, that becomes thorium 234. And the reason why you take two from here and you take 4 from there, because the bottom number, this is the proton number, and since there's only 2 protons, you take 2 away. And this is protons and neutrons, so you take 2 protons and 2 neutrons, so you take 4 away. And then you get thorium 234. There is also radon 226, which decays also via alpha decay, which becomes, radium becomes radon, not radon. Becomes the element radon, which is a noble gas. There's also something I'm going to show you which will make sense for everything later. A neutron has a relative mass of approximately 1. If you've ever heard, so a proton has approximate mass, mass 1, but neutron is actually just a little bit greater mass than a proton. That is because a neutron is comprised of a proton, electron, an electron neutrino, and the electron neutrino. And you express it kind of like, there it is, like this. So, proton positive plus electron plus anti-electron neutrino gives you a neutron. Because neutrons, if they are on their own, they decay into proton, electron, neutrino. But in 1 in 100 cases of a neutron decaying, it can form a proton, electron neutrino, and a gamma. That's if that neutron is possibly absorbed the gamma and it's slightly more energetic. It gives you just a neutron. So with that, if you have, so let's say you have, let's say we have beta decay. We have some nucleus. So there's 2 forms of beta decay. There's beta decay and anti-beta decay, which has a positron set of electron and a normal electron neutrino. The same principles apply. So if we have fluorine 18 decays via an anti-beta, which means you get oxygen 18. So in nucleus, what's happening is, so we have further, so we have 9 protons, 9 neutrons. One of the neutrons ejects. Oh, hold on. One of the neutrons ejects an electron, or positron, and just a normal electron neutrino, becoming proton, thus giving you oxygen 18. Now, gamma radiation, it's often not a type of decay that is just by itself, and is more often than not accompanied by another type of radiation, like it will go gamma then alpha, or alpha then gamma, or beta then gamma, gamma then beta, or so on and so forth. But there are elements that decay from prominently gamma, or it's noticeable. So cobalt 60, one of my favorite isotopes. Actually, I think it's my favorite isotope. Is still just itself. It hasn't changed. But it has changed, it's just not necessarily noticeable. All it's done as it's reduced its energy state to make it more stable, because that's really what decay is. Now, delta radiation. Delta radiation is when an atom decays via a neutron. So, for example, bromine 87, which becomes bromine 86. Same element, smaller isotope. Neutron radiation is one of the strongest. It's super powerful penetrating power. It may just be a particle, because gamma, it makes sense why it's very, very strong, because it can penetrate through solid matter. Hold on, I'll be back in just a sec. Oh, sorry, I just had to get some water. Anyway, so neutron radiation has very, very good penetrating power. Gamma has very good penetrating power because it's not technically solid. It doesn't have mass because it's a photon, so it's very easily, it can pass into the nucleus or pass through an atom. While neutron, since it actually has mass and it's solid, it's a little bit more difficult, but it's still very, very fast. Now we have epsilon decay, which is also known as something called electron capture, which is when, if we have, let's say we have a nucleus, and it needs a neutron. It's proton efficient and needs to be equal to neutrons. What it can do is it can absorb an electron into a proton, giving out an electron neutrino. So P E gives you electron neutrino. This radiation, this type form of decay is fairly rare, but it does happen. Okay. An example is indium, well, actually no, I'll do gallium to zinc. So gallium 67 becomes zinc 67, except The only thing that's changed is actually the proton number, because obviously the protons become a neutron and it decays via and gives you a neutrino. And now the last one, which decays by ejecting a proton, so that's zeta. It's alright. So it decays via a proton, because again it's proton efficient. So unlike the last one, it's proton efficient but not too much proton efficient where it needs to, because that one you're minusing a proton while adding a neutron, which is kind of like removing two protons in a way. While this, because I'll show you why. So if we have A over B, we have the ratio between A and B, you take away from A and you add to B, that basically becomes A ratio plus 2. Anyway, an example of ejecting a proton is, well, here, so I've got a special one here. So there's there's cobalt 53, which becomes iron 52. There's also another one, because in all of these there's a special form of them where there's like specific names given to if you have like a gamma, a beta and an alpha, they all decay subsequently or at the same time. Or you can have double proton decay, where instead of absorbing an electron and making a proton into a neutron, it ejects two protons, which is iron 47, which becomes chromium 45. Also, a thing I would like to show you is if we have, so we have paper, so paper, alu foil, I think, oh wait, no, yeah, foil, glass, and then like concrete / lead, I think it is. We have alpha, beta, gamma, and delta. Alpha can just penetrate paper. Beta can penetrate paper and like some like metal foil, but it can't really go much further than that. Gamma can penetrate all of these and can also penetrate glass, while neutrons can penetrate all of these and just about concrete and lead, but after a certain thickness. So yeah, that's all for today. Bye.